Welcome to your first video on our last unit, which is called Probability Distributions. This unit is going to be combining the probability that we learned in Unit 2 with a little bit of counting from Unit 1, as well as the statistics we learned in Unit 3. A lot of what we're going to be doing in this unit is not new, but some of it will be new. Some of it will just be the same as what we were doing before, but just a faster way of doing it. So a couple of definitions before we start. A probability distribution is a display of the probability of all the possible outcomes within the sample space. So that what that means is that before we would say a die is rolled, what's the probability of rolling a 4? In this unit, with a probability distribution, we don't want to just know what the probability is of rolling a 4, we want to know what the probability is of rolling all of the possible outcomes. So what's the probability of rolling a 1, what's the probability of rolling a 2, what's the probability of rolling a 3, all the way up to what's the probability of rolling a 6. The expected value is the mean. So that's just your X bar. So on average, if you were to continuously roll this die, what would you roll on average? So probability distribution is display of the probability of all possible outcomes, and the expected value is the mean. So we're going to start with a really easy example. And in this first example, we're going to be rolling a 6-sided die. So to be able to make a probability distribution, there's two things you need to know. The first thing you need to know is what is the variable that's being measured. The variable that's being measured we usually represent with a capital X. And in this case, the capital X, what we are measuring is the number rolled. The second thing you need to know is what are all of the possible outcomes in the sample space. Each of these outcomes is labeled with a little x. So this would be little x outcome 1, little x outcome 2, little x outcome 3, little x outcome 4, little x outcome 5, little x outcome 6. So the big X is in words what is the variable being measured. The little x represents each of the possible outcomes. So those are the two things you need to know. There are three ways to represent a probability distribution. The first way is to just list them out. So the probability that the number rolled is a 1 would be 1 over 6. The probability that the number rolled is a 2, 1 over 6. Probability that the number rolled is a 3 is 1 over 6. And they all happen to be 1 over 6. And sorry, a little mistake here. This should be x equals 6 for your communication. Now, having to write out px equals all the time is a little bit annoying. So what you could do is list it in a table. In the first table is the little x, and these are your outcomes. And in the second column is the probability of each outcome. So make sure you're titling the each column properly. So this is little x, so the outcomes are 1 through 6. And the probability that the number rolled is each of the values of the little x. So if little x is 1, the probability is 1 over 6. If little x is 2, the probability is 1 over 6. In this case, they're 1 over 6. The third way that you could represent a probability distribution is to use a graph. So in this case, the horizontal axis is the outcome. The vertical axis is the probability. Make sure that they're labeled the same way you would in the table. And then for each of the outcome, you can use a bar to show that what the probability is. Now, this data is discrete because You can only roll a 1, 2, 3, 4, 5, 6. You can't roll a 1.5. You can't roll a 1.24. So if it's discrete, then you can use a bar graph. Later on, when we get to continuous data, you would have to make a histogram. And we'll get into that later on in the unit. But for now, we're going to just deal with discrete data. So your graph can be a bar graph. So we're going to do a couple of examples, and these examples you have seen before in your Unit 2. So determine the probability distribution and expected value of rolling a 6-sided and a 4-sided die. So if we roll a 6-sided and a 4-sided die, that means we can roll anything from 2 up to 10. So in our table, our possible outcomes are everything from 2 up to 10. So because we're making a probability distribution, we need all outcomes. Now we have to find the probability of each outcome. But before you do that, just like all probability, you have to define what the variable x is. So we're going to say, let our variable represent the sum of the two dice. So just like in probability unit 2, you have to give your let statement of what letter you're going to use. So rolling a 6-sided and a 4-sided die, that means the number of outcomes in the sample space is equal to 24, not 36, because it's not two 6-sided dice. So the probability of rolling a 2 is just 1 out of 24. The probability of rolling a 3 is 2 out of 24. And you could put this into lowest terms, but for later on, it's a little bit easier to keep it as the same denominator, and you'll see why later. The probability of rolling a 4 is 3 out of 24. The probability of rolling a 5 is 1, 2, 3, 4 out of 24. The probability of rolling a 6 is also 4 out of 24. 7 is also 4 out of 24. Probability of rolling an 8, there's 3 of them. For a 9, there's 2 of them. And for a 10, there is 1 of them. And then because our probability scale is usually in decimals, what you're going to do is change each of these into a decimal. So there is all of your probabilities written as decimals. And then now we're going to make a graph. So the probability of rolling a 2 was 0.04. And that was also the same as the probability of rolling a 10. And the probability of rolling a 3 was 0.08. And a 4 was 0.125. And a 5 was 0.17. And this was 0.17. And 0.17. 0.125 and 0.08. there's your probability distribution as a table and as a graph. For the next couple of examples, we're going to go back to Unit 1 and 2 where we dealt with counting and probability. So a bag contains 8 blue and 12 red marbles. 2 marbles are drawn and replaced, so that's important because that means we have independent events. And determine the probability distribution and expected value of the number of red marbles drawn. Draw a tree diagram and label the probabilities to help. So remember, the two parts that you need to start the probability distribution is to first state what your variable represents. So because we're eventually going to be finding the expected number of red marbles drawn, that's a good place for us to let our x be. So x is going to be equal to the number of red marbles. And after we know what our x can be, or x represents, you also need to know what the possible outcomes are. So you can have, remember all of this is in terms of red marbles. So we're looking for the probability that the number of red marbles is 0, the probability that the number of red marbles is 1, and the probability that the number of red marbles is 2. And we do that by using this tree diagram. So there's 8 blue and 12 red marbles, so that means the number of marbles in the sample space is equal to 20. So if there's 8 blue, the probability of drawing a blue is there's 8 of them in favor out of a total of 20. And the probability of drawing a red marble is 12 favorable marbles out of a total of 20. In the first round, there is an 8 out of 20% chance, or 8 out of 20 chance of getting a blue marble, and a 12 out of 20 chance of getting a red marble. Because we are replacing the marble, that means the events are independent, so the probabilities don't change. So once again, there's still 8 blue marbles out of a total of 20 for the second draw. And there are still 12 out of 20 marbles for red for the second draw. And that's your tree diagram. So to find the probability that the number of red marbles is equal to 0, that would mean you'd have to get 2 blues. So here is the case where there is no red marbles. So that means you would have to draw a blue and a blue. And in lowest terms, that works out to 4 over 25. And as a decimal, that is 16%. So you only want the decimal for the graph, but otherwise you would just leave your answer as a fraction. Now, for 1 red marble, the probability of getting 1 red marble means you could get a blue and a red. So here is an example where you'd get 1 red marble, or you could get a red and a blue. So here's another example or a case where you could get 1 red marble. So in this case, we have a blue and a red, or a red and a blue. So you can multiply and add all of these, or because they're the exact same thing, you can just do 8 over 20 times 12 over 20 and multiply it by 2. Either which way, in lowest terms, that gives you 12 over 25, which works out to 0.48. And for two red marbles, that's just this case, which means you can have a red and a red. So the probability of two red marbles is a red and a red, which is in lowest terms 9 out of 25, which is in lowest terms 0.36. So you don't have to draw a chart, but if you did want to draw a chart, then this would be x, and this would be the probability that the number of red marbles is equal to each value of little x. So for 0 red marbles, we had 4 out of 25, which is 0.16. For 1 red marble, we had 12 out of 25, which is 0.48. And for 2 red marbles, you had 9 out of 25, which is 0.36. So to make the graph for 0 red marbles, we had 0.16, and then we had 0.48, and then we had 0.36. So there's your probability distribution graph. Now, with the expected value is the same thing as the mean. And if you remember, the formula for the mean is the sum of each value of x multiplied by its frequency divided by the sum of all the frequencies. So in probability, instead of using x bar as the mean, we use EX, and this is just a symbol that means expected value, which is the same as the mean. And in this case, well, this is the x that goes in here in the formula, and the probability is the frequency. It's just that it's a relative frequency instead of an absolute frequency. So what we do is we have to take each value of x, multiply it by its frequency, and we have to add them all up. Now, these were terminating decimals, so you could use the decimals, but usually these are rounded decimals, so you would want to use the fractions as your frequencies. So an outcome of 0 red marbles has a frequency of 4 over 25 plus an outcome of 1 red marble has a frequency of 12 out of 25, and an outcome of 2 red marbles has a frequency of 9 out of 25. And this is all divided by the sum of the frequencies. If you were to add all of these up, 4 out of 25, 12 out of 25, and 9 out of 25, the sum of all the frequencies is equal to 1. And it will always be equal to 1 because all of them together is going to equal 100%. So really, this part of the formula isn't even really necessary because that's always going to equal 1. So you really just have to do this top part. 0 times 4 over 25 plus 1 times 12 over 25 plus 2 times 9 over 25 gives you, in lowest terms, 6 over 5, which makes 1.2. So on average, the expected number of red marbles is 1.2. That means if you were to repeatedly draw 3 marbles, on average, you would draw 1.2 red marbles. Now I know you can't draw a 0.2 of a marble, but we do leave it as a decimal because when dealing with averages, we do allow the decimal. So there is an average of 1.2 red marbles that would be drawn. Now to ease your calculation, because all of the denominators are 25, and I said why sometimes you want to leave the denominators the same, instead of going 0 times 4 over 25 plus 1 times 12 over 25 plus 2 times 9 over 25, to make your calculation easier, you can just do 0 times 4, which is just 0, plus 1 times 12, which is just 12, plus 2 times 9, which is just 18, press equals, and then just divide by 25. So it's just something that's a little bit faster for you. So let's take a look at this next example. It's basically the same example, but in this case we are having no replacement. So we have 6 men and 8 women. That means the number of outcomes in the sample space is 6 plus 8, which is 14. So that means the probability of a man is 6 out of 14, and the probability of a woman is 8 out of 14. Now, we're going to determine the probability distribution and expected value of the number of men on the team. So that means our random variable should be the number of men. And we are forming a 2-person team. So once again, that means you can have no men, 1 man, or 2 men. So the probability that the first person is a man is 6 out of 14, and the probability the first person chosen is a woman is 8 out of 14. Now, once you choose a person, you can't choose them again, so this is non-replacement. That means to choose the second person, you now only have 13 people to choose from. And if the first one was a man, now there's only 5 men left, but there's still 8 women. If the first one was a woman, there's only 7 women left, but there are still 5 men. So, for our probability distribution, the probability of no men means we'd have 2 women. So this time, no men is over on this side. So that means you would have a woman and another woman, and in lowest term, that works out to 4 over 13, which is approximately 0.31. So for 1 man, you could have a man-woman or a woman-man. So the probability of 1 man is man and woman, or woman and man. So there's man, woman, or woman, man. Oops, just realized that should be a 6. Alright, so that works out to, in lowest terms, 48 over 91, and that is, approximately equal to 0.53. Lastly, 2 men. So the probability of 2 men would be a man and another man, and that works out to 15 over 91, which is approximately equal to 0.16. So that's your probability distribution. So to make the graph, so 0 men would be 0.31. 1 man was 0.53. Oops, sorry, that's a little bit off the graph. And 2 men is 0.16. So there is your graph and your expected value. So remember, for expected value, you were looking at the first outcome, which is 0, times its probability, and make sure you use the fraction and not the decimal, because the decimal was rounded. So you have to use the fraction. So the outcome of 0 men had a frequency of 4 over 13. The outcome of 1 man had a frequency of 48 over 91. And the outcome of 2 men had a frequency of 15 over 91. And remember, you're dividing that by the sum of all the frequencies, which is just equal to 1. So that works out to, in lowest terms, 6 out of 7, which is approximately equal to 0.86. So that means the expected number of men is approximately 0.86. Okay, the last couple of examples here you might get. The average length of stay in a hospital is useful for planning purposes. Suppose that the following is the distribution of the length of stay in a hospital after a minor operation. The number of nights do not exceed 4. So the only possible outcomes are 0, 1, 2, 3, and 4. So it is, what is the probability of staying 3 days? So first thing we need is our random variable. So x equals the number of days spent. And what you want to remember is that all of the probabilities have to add up to 1. So to figure out something that's missing, so the probability of staying 3 days is going to be 1 minus all of these other numbers. So 0.4 minus 0.2 minus 0.2 minus 0.05, and that works out to 0.15. And the average length of stay is the same as the expected value. So this is your probability distribution. So this question didn't ask you to make the probability distribution. You just had to fill in the missing information. But now the average length of stay, remember that this is the data, the outcomes, and these are the frequencies. So the expected value is the first outcome is 0 and its frequency is 0.4. The next outcome is 1 and its frequency is 0.2. The next outcome is 2 and its frequency is 0.2. The next outcome is 3, frequency is 0.15, and the last outcome is 4 and its frequency is 0.05. And of course all of that is just divided by 1 because that's the sum of the frequencies, and that works out to 1.25. So the average length of stay is 1.25 nights. And again, because it's an average, you're allowed to have a decimal. All right, the last question deals with a game, and we're going to use more examples with games in the next lesson that you do. So a game consists of rolling a die and or drawing a deck of cards and or flipping a coin. If you roll a 1, you are out and you win nothing. If you roll a 2, 3, or 4, you draw a card. If you draw a face card, you win 20, otherwise you win nothing. If you roll a 5 or a 6, you flip a coin. If you flip a head, you win 15. If you flip a tail, you lose 10. Determine the probability distribution and the mean amount of money won. So, sounds a little overwhelming. So, the best thing to do with these games is to start off with a tree diagram. So the first thing you're going to do is roll a die. And in this case, there's really only 2 outcomes. There's not there is how many outcomes? You roll a 1, a 2, 3, or a 4, 5, or a 6. So there's 3 outcomes. So in the first round, there's 3 outcomes. You can roll a 1, you can roll a 2, 3, 4, or you can roll a 5 or a 6. So the probability of rolling a 1 is 1 over 6. The probability of rolling a 2, 3, or a 4 is 3 over 6. And the probability of rolling a 5 or a 6 is 2 over 6. So the next thing you're going to do is, if you roll a 1, you're out and you win nothing. So what you're going to do is that terminates that branch and you win nothing. So what we're going to do is when a branch terminates, you're going to write down how much money they win. So that branch, if you roll a 1, you're out and you win nothing. If you roll a 2, 3, or a 4, you draw a card. And you're either going to draw a face card or you're not going to draw a face card. So there's only 2 outcomes here. So a face card and not a face card. So if you draw a face card, that probability is 12 out of 52, and the probability of a non-face card is 40 out of 52. If you draw a face card, you win $20. So that's the end of that round. So we win $20. If you do not win a face card, you win nothing. So that ends that, and you come out with $0. Lastly, if you roll a 6, you flip a coin. So with a coin, you can flip a head or a tail. And the probability of a head is 1 over 2, and the probability of a tail is 1 over 2. If you flip a head, you win $15. So that branch terminates with winning $15. And if you flip a tail, you lose $10. So that would actually be negative 10. So when you have a game, you want to draw a tree diagram, and then you can figure out all of your outcomes. So we could lose $10, you could win nothing, you could win 15, or you could win 20. Usually we put them in ascending order here. So X here is actually representing the amount of money won. So the probability of losing $10 means you have to flip a 5, roll a 5 or a 6, and flip a tail. So to calculate this probability, we have to roll a 5 or a 6, which is 2 over 6, and flip a tail, which is 1/2. And that works out to 1 over 6 in lowest terms. Now you don't need to put the px equals -10 here, because that's the point of arranging it in the table, is we've listed all of our x's and we've stated that anything in this column is the probability that the amount of money won is equal to whatever that little x is. So this is the probability of losing $10. And then what I like to do is put a little check mark there saying I've taken care of that branch, because later on when we get more complicated games you're going to have tons of branches. Now the probability of winning $0 means you could roll a 1. So one way to win 0 is to roll a 1, and that probability is 1 over 6. But we also have another case, so it's or. The other way to win nothing is roll a 2, 3, 4 and not get a face card. So rolling a 2, 3, 4 has a probability of 3 over 6, and getting a non-face card is 40 over 52. And in lowest terms, that works out to 43 over 78. Probability of winning $15 is this branch, so you'd have to roll a 5 or a 6, which is 2 over 6, and get a head, which is 1/2. So that works out to 1 over 6. And the probability of winning $20 is rolling a 2, 3, 4 and getting a face card. So the probability of a 2, 3, 4 is 3 out of 6, and a face card is 12 over 52. So that will work out to 3 over 26. Now one way to check to see if your work is correct is to add all of them up. Now if you add them all up, they should equal 1. So when you do, take all of those and add them together. So 1 over 6 plus 43 over 78 plus 1 over 6 plus 3 over 26, you get 1. That doesn't ensure that you did it correct, because you still could have made a mistake somewhere or made a couple of mistakes that balanced each other out. But if that does not equal 1, then for sure you've made a mistake. And the expected value, an outcome of -$10, has a frequency of 1 over 6. An outcome of $0 has a frequency of 43 over 78. An outcome of $15 has a frequency of 1 over 6. And an outcome of $20 has a frequency of 3 over 26. Dividing all that by 1, that works out to approximately, this is money, so $5.64. So round to 2 decimal places because it's money. So on average, a person, or we should say a player, will win $5.64 per play. So every time they play the game, on average, they will win $5.64. So that concludes our lesson. If you have any questions, please make note of it and ask your teacher in class tomorrow. Thank you and goodbye.